Hello, listeners. My name is Rob, and I am here virtually alongside my usual co-hosts Noah.
Hello.
And Emily.
Hi.
The regular cast of Fax Machine, a podcast by and for people who are curious about everything, but especially the things that make them laugh. And today, I'm very pleased to be welcoming our special guest and longtime friend of the podcast, Jessica Noviello.
Hello, everybody.
Yeah, so astute listeners will know this is the first time that we've ever had a guest at a non-live episode. Also the first time we've ever had a guest in a remote episode. So a lot of firsts today. No pressure.
Oh, I'm so honored. Are you kidding me?
Jess, you've actually been mentioned in our episodes, dating back to when was that, like number 5? One of our first 5
Yeah,
episodes?
I think it was multiple times. There was number 2 with Rise and Shine. I got in touch with Jessica to ask a lot of questions about like geology. And she told me that to like really answer the question, I would have to understand fourth order differential equations, but she'd try her best. And so I was like, okay, well, explain it like I don't know any order differential equations. And then there was another time I think we talked to you about it was icy chaos or something on Europa.
Yes.
And so you were a very helpful contributor for some of our cool science facts that were a little out of our league, especially when it came to ice.
Well, I'm always happy to help the podcast. You guys are awesome.
And Jess, can I ask, like, what is it that draws us to you about icy space things? Is there any reason that Noah has chosen you as his go-to person, or can you tell us a little bit about yourself?
I mean, I might just be the only person he knows who studies space ice, but I want to think I'm a good person to know, even if I'm the only one. So I finished up my PhD in a field called planetary geology last June, so this is June 2019. And I studied Europa, its small-scale geology features like chaos, which we've talked about, and listeners, you can go back to that podcast and listen about that. So I finished up my PhD last June, and I studied the geology of Europa, and I spent literal years doing nothing but studying Europa's geology. So I definitely know a thing or two about it. But what's funny is that I did not even know planetary science was a thing, a scientific field, until college. So it was just by accident that I kind of stumbled into it. And I'm really happy that I did, don't get me wrong. But what's funny is that I went into grad school expecting to study asteroids because most people who know me know I love dinosaurs. They're number one favorite scientific topic. Sorry, Europa. But an asteroid killed the dinosaurs. So I was like, whoa, that thing is more powerful than a dinosaur. I'm going to study those. And that project, I ended up switching projects, and then I did Europa, and now I kind of do asteroids, Europa, exoplanets, and a bunch of other things too. SciComm being one of them. So I'm kind of all over the place in terms of my research, and the one connecting thread that I can think of is water. You know, how water has affected all of these bodies, how water is on some of these bodies, whether it's on the surface like Europa's ice shell or locked up in a mineral like on certain asteroids. So I know water.
Well, that's good.
Nice.
That is very lucky, because this is an episode that is all about what, Rob?
Oh, it's going to be all about water. And I just want to jump in
what
with
a
one
stroke of luck.
How did that happen?
Yeah, this is going to be an episode that is just dripping with water facts, water references, hydrodynamic conversations. But even if it's a soundbite we throw away, I just wanted to ask Jess, in a primordial game of rock, paper, scissors, that would be dinosaurs, asteroids, water, in which I presume asteroid beats dinosaur, water beats asteroid. Do you think dinosaurs beat water to complete that circle, or?
No, water beats everything.
Okay.
Eventually.
There we go.
I think water is, effectively rolling a natural D20 during a game of Dungeons and Dragons. Like it is bad news if you are a rock or a dinosaur who cannot swim.
Or if you're especially pruny.
Or especially pruny.
Yeah.
Pruny. I can speak. Sorry, I haven't had that much scotch yet.
The more
get
you
on
have,
that, the better it gets.
And while Jessica chugs scotch.
That's wonderful. Because while we're distancing in remote locations, we're happy to bring you an episode all about water. So each of Noah, Em, and Jess are going to bring you one fascinating fluid fact, just sopping with science. And I'll finish things up with a pub-style trivia quiz, loosely inspired by the theme. And so, if we have nothing left to add, or preamble in this episode, let's get started with Noah.
Thanks, Rob. This week I learned that Nobel Prize-winning physicist Niels Bohr stored the heavy water he needed for his atomic research in a beer bottle in order to hide it from the Nazis. So,
what brand of beer, I guess, is the big question?
Well, it was heavy water. So it wasn't beer. Although it maybe we'll come back to that. So basically, I mean, Niels Bohr is a physicist. Probably most well known for his sort of what they call a model of the atom, which basically had been developed at that time. It had gone from something that I think J.J. Thomson came up with, was this idea of the quote-unquote plum pudding model, where basically I think he's thought of it as like a little positive like thing in the middle, and the electrons were like the raisins in the plum pudding. It was a weird analogy, but that's what you have to do in order to like push through those kind of weird analogies to get to true scientific understanding. And there was another one, I think this was Rutherford, and that sort of got a step closer, and then our friend Niels Bohr advanced on that, and basically his idea was this concept of electrons being in these different energy states. So this idea that they could be in these different energy states was a unification of this previous atom model with a lot of the sort of quantum research that was coming out at the time. And so he is Danish. He was also the son of a Jewish mother and also a non-Jewish father whose first name actually was Christian, which is interesting. And he, did his master's and his PhD, and then went to do research, and eventually, as I said, was talking about this particular model of the atom. He published in 3 papers that are called collectively were called the trilogy. Which was kind of an awesome way to like refer to like 3 papers which like had this big crazy groundbreaking theory.
I'm jealous.
Yeah, right.
I have to know, did he call it the trilogy, or did
I don't know.
So because that really changes my perception of it.
It's just referred to as the trilogy, but I would love to have 3 papers. I'm working my ass off. I'm still almost to that. But yeah, so he was doing really well, and he began to be more well known. Of course, he won a Nobel Prize. He was an eminent physicist at this time when a lot of other really dark stuff was about to happen in the world. And the fact that he was a nuclear physicist, essentially, or at least an atomic physicist, made him a central figure in a drama that played out. And that was basically the aspirations of both the Axis, particularly Germany, and the US and the UK trying to develop nuclear weapons. So in 1933, after the Nazis came to power in Germany, a lot of German scientists who opposed the Nazi regime fled to Denmark, and Bohr was one of the people like helping them escape, basically. And quite a lot of these people, these included Edward Teller, James Franck, Otto Frisch. A lot of them went on to work for the Manhattan Project, as a lot of the physicists of that time did. So in April 1940, the Nazis actually invaded Denmark and occupied it, and there was like a pretty high-profile meeting now in sort of the history of the nuclear programs, where Heisenberg, who was the head of the German nuclear program, and I think was sort of maybe even that Bohr had been his mentor or something.
Are you sure about that?
Oh, nice. Well, I read in all these articles. That's great. I read in all these articles that they went on this like long stroll in some park in Copenhagen and had a conversation. But I couldn't figure out where this park was and when the conversation happened at the same time. I could only get one of those pieces of information.
There it is.
I was completely on board with you not knowing the time or the place, and then I realized it was a joke.
Yeah.
Which is kind of embarrassing. I was a physics major.
Oh no. Well,
I believe you.
Well,
so
the thing
much.
is that is the extent that I understand about Heisenberg uncertainty principle. I am, in fact, uncertain about everything else in quantum mechanics. So we'll have to rely on you for that.
So is everybody else.
But so there was this situation where nobody knows exactly what happened. Some documents have like surfaced recently about maybe like letters that were sent after the fact. People are trying to piece together what Heisenberg and Bohr actually talked about. But in general, the idea is that Heisenberg was trying to recruit Bohr, or like at least like get some information out of him to try to figure out how they could advance the German nuclear program. But it became clear after that meeting that Niels Bohr was not safe anymore. And he then had to be in this like crazy adventure. He had to be like extracted from Denmark by like special forces with the Danish resistance fighters and stuff. And I'll tell you that story in just a minute. But first, I want to tell you how that would not have been Niels Bohr's first like foray into espionage like activities. So he had a little primer in this. So one particular story, I mean, obviously when he was helping all these scientists escape, but one particular story I think really paints a good picture of what it was like to be scientists who were trying to like pull one over on the Nazis. So this particular story is about Max von Laue and James Franck, who are both German, and they won the Nobel Prize in Physics in 1914 and 1925 respectively. So von Laue openly opposed the Nazis, and Franck was Jewish, so they were clearly in danger. And the Nobel Prize, as everyone knows, is basically this big gold medal with your name on it. And so both men, when in their escaping Germany through Copenhagen, left their medals with Niels Bohr for safekeeping. But then the Nazis occupied Denmark, and basically there was this concern that the Nazis would then find the gold, and besides sentimental value, you don't want Nazis to have gold. It's just a general thing you should try to keep away from them.
Isn't that an Indiana Jones plot point?
I was going to say, it's an entire subplot. Actually, no, it's a main plot.
Was Niels Bohr Indiana Jones?
I think so, yeah. I mean, fights Nazis.
Whoa.
That's it.
Steals their gold.
Wow. So he got two
protects gold from them.
Did he hate snakes?
Oh, that's the deciding factor.
Ooh, I don't know.
Yeah.
Yeah. Here's what I got was there's the Hiss orbital.
Well, the person he didn't like in his field was Hissenberg. So it's perfect. So we've established Niels Bohr is Indiana Jones.
Hates snakes.
Have you ever seen them in the same place at the same time? No.
I mean, they would have been contemporaries, which is really fun. I kind of want to say, oh man. Okay, so they did Kingdom of the Crystal Skull, which was horrible, and I don't want another Indiana Jones movie. But incorporating something with Niels Bohr escaping Denmark, man, that would have been a missed opportunity.
Maybe if they did it as like a buddy comedy of like
him
and Indiana.
But it turns out like in the end that it's like Fight Club and they're the same person.
And then Heisenberg's like, ha.
Niels Bohr isn't here right now. Niels Bohr went away. Niels Bohr's gone.
We've put Niels Bohr inside of a sealed casket with a vial of poison. Is he alive or dead? Or when you open it, you don't know whether Niels Bohr is still Niels Bohr or is now Indiana Jones.
Well, if it was Indiana Jones, wouldn't he have escaped?
Oh,
so you don't even know.
Well, you would think it was. That's
Or is that Houdini?
Maybe.
Don't. We don't need to be more complicated.
Wait,
this is already unsalvageable.
Houdini might have been dead by this time, or was
I think he was. Yeah.
Or was he? Exactly.
Punched in the stomach by a Nazi snake. Okay, but just going back to a different completely true definitely happened story. So Max von Laue and James Franck escaping, they left their gold medals from the Nobel Prize with Bohr, right? And so Bohr was like, how do I keep them from the Nazis after they occupied Denmark? So his first idea was to bury them, but he was like, no, the Germans are just going to dig up and find them. That's what they do. They dig up precious metals from other people, like just like Indiana Jones stops them. Anyway, but there was actually a Hungarian chemist who worked with him, whose name I will not attempt to pronounce in full, but his last name is, I think, Dehevzi. So we're going to leave it at that. He also worked at the Bohr Institute, and he realized that he could actually dissolve the gold in a solvent. And so it turns out that gold is actually quite difficult to dissolve, but there is one substance that was known that it could do it, and it's called aqua regia, which I think is royal water, I guess. Yeah. And also part of our water fact, which is one of the reasons I included this, and that can do it. And that's basically like hydrochloric acid and what is it, like nitric? Oh my god, acid, I just looked it up. Nitric acid, yeah, hydrochloric acid and nitric acid, in like a 3-to-1 or 4-to-1 ratio, and it's capable of doing it. So basically they dissolve the gold medals in like these two different beakers into this aqua regia, and then the Nazis did actually get there and search the entire institute, but they ignored this like beaker of like this orange tinted liquid that was literally full of liquid gold. And what was great is that after, eventually, as I'm going to tell you the story, Bohr did flee Denmark, and Hevzi left for Sweden, but he returned to Denmark after the war, and the beaker was still there, undisturbed, intact, and they actually managed to like extract all the gold, send all that gold back to the Nobel Foundation, and the Nobels recast new medals using the original gold and gave them back to the Nobel Prize winners who had to flee Germany, which is a very cool result. Yeah.
Wow.
But as I've mentioned now a couple times, Niels Bohr had to flee himself, right? So Niels Bohr was basically always going to be in danger from the Nazis. One of the reasons was because, obviously, he was Jewish, or part Jewish. Another reason was of his incredible value as, like, an atomic scientist when they were, really interested in getting all the knowledge they could about that in order to develop a nuclear weapon. And one of the things that was, in addition to just, like, the brain power they needed to do those kind of things, was the actual materials that were necessary in the refinement of, say, like plutonium from uranium-238. And one thing that's really important for that process, there are a couple different ways you can go, but the Nazis chose to use something called heavy water. And heavy water is basically, you've got, instead of just regular hydrogen atoms in your H2O, which would be a hydrogen atom attached to an oxygen, that oxygen attached to another hydrogen atom, right? The hydrogens in this basically water molecule also have a neutron. So a normal atom of hydrogen, it's just a proton and an electron orbiting it. This is a hydrogen atom for most intents and purposes, but it's basically twice as heavy, and it has some subtly different chemical properties. One of the things it's really good for is that it has the ability to slow down neutrons that are ejected whenever neutrons are ejected. You know how neutrons are, and this is really important in basically making, if you want to I guess it's important to slow neutrons down so that they can more efficiently interact with the nuclei of other atoms if you want to create a slightly larger atom, like moving uranium-238 to plutonium, which is slightly bigger. So it was really important to try to get large quantities of this heavy water. It was difficult to produce. You basically had to isolate it from just water that was out in the world. I think it's something like 1 per 20 million water molecules is a heavy water molecule. They have slightly different boiling temperatures, so you can distill them, I guess, but that requires a lot of energy to make the water boil. So there are other chemical methods that you can use to isolate them. But you needed big plants that would do this. And of course, in addition to being useful for developing nuclear weapons, it was also very useful for atomic research in general. And someone like Niels Bohr, who had the whole Bohr Institute dedicated to this particular thing and was a Nobel Prize winner and a leader in his field, had some of it lying around. And this, of course, was concerning because it was very, very valuable. He didn't want it to fall into the hands of the Nazis. It was necessary for the British Secret Service to extract him, literally, from Denmark under the cover of night. So basically, Niels Bohr was told to be at a particular pier at the harbor in Copenhagen at a certain hour of the night, and the idea was to try to smuggle him out to Sweden. So basically, he was like the Danish resistance, for like the ones who kind of were like on the ground, and they come, they like bang on his back door, they're like, it's time. He is like rushing out the door through his kitchen apparently, and he realizes that he has this, as I mentioned in the fact, he was taken to, in order to like protect this heavy water, he had taken to filling up like a beer bottle with this heavy water and storing it in his like refrigeration refrigerator, I guess, in a chilled, controlled environment. He had these bunch of bottles of beer. I think the way that it's described later, I think they were like growler sized, basically. So it was like a big bottle, and he had a bunch of them. Most of them had beer in them, but one of them was just full of this like priceless heavy water. And so as he's like
Danish roulette, I think is what you call it.
Exactly. But as he's like escaping the house, and the Danish resistance are like looking around with their guns, they're like covering the area, he was like, oh wait, I have to bring this bottle. And so he runs out of the house carrying this big giant like bottle of beer, and the Danish resistance fighters are just like, what are you doing? You like went back for this big jug of beer? Are you crazy? They have beer in Sweden. Like, what are you worried about?
It's small batch. She just runs by.
Support your local brewery.
Yeah. Well, his local brewery was Carlsberg, actually. And another thing that was interesting about beer in his house is that when he won the Nobel Prize, Carlsberg actually bought him a house next door to the brewery and gave him a direct tap to their beer.
No.
And I think that's probably a good moment in the middle of this harrowing espionage story to say I'm actually drinking Carlsberg premium Danish Pilsner right now.
Perhaps the finest lager in the world.
Hashtag.
Perhaps, I think they say probably the best beer in the world. That's what it says here. And I think they're saying that like statistically significant probability. Anyway, so that's pretty cool. So he could actually, he was probably filling that up with Carlsberg like straight from the Carlsberg tap on his wall. So there was no shortage of it, I guess. Maybe anyway, they were very concerned that this was his priority, was to bring this beer, because they didn't know what the heavy water was. So he's like, they're like, whatever. So they're running through like the streets, probably like shooting behind them just like Indiana Jones would. And it actually, apparently the Nazis did actually like raid the house, I think like very soon after that. So they were like hot on their heels. And they got to the boat, they got out, and they managed to like get him to Sweden. And it was the first thing he did was to go to the Nobel Institute to actually meet with Dr. Lisa Meitner. Basically, the story goes, in the book, Burn After Reading the Espionage History of World War II, it says that he handed her the bottle to basically like keep safe at the Nobel Institute and maybe she could use. And then Dr. Meitner basically like examined it and was like, it says she exclaimed in a voice of anguish that it was real beer. That it wasn't the heavy water bottle. He had accidentally grabbed just one of the other identical beer bottles that had beer in it. So the heavy water was still in the house, still camouflaged as beer. And the story goes basically that it's also from this book. For the next 24 hours, that confounded bottle became the most important target for the Allied secret services. A team of the Danish underground sneaked into the abandoned Bohr house, reached the icebox without incident, took the important bottle, and smuggled it safely to Bohr in Sweden. So they never did understand why they had to go to so much trouble just to get a bottle of Danish beer for a bibulous old professor, which is a great thing. Anyway, Niels Bohr was a crazy spy scientist badass who almost died 1,000,000 times, but nonetheless gave us a very cool model of the atom and a great story about heavy water.
And was possibly Indiana Jones.
And was 100% Indiana Jones.
Well, there you have it.
Within the error bars.
So this week I learned that last summer, a group of scientists at Columbia published that they found a huge reservoir of fresh water in probably the last place you'd think to look for one, under the freaking ocean. So this fact comes from a paper that was published in June of 2019 in the journal Scientific Reports, but the actual story of this discovery starts way before that, back in 1976. So that was when the U.S. Geological Survey conducted the Atlantic Margin Coring Project, or AMCOR for short, to survey an area of the continental shelf along the northeastern coast of the U.S. And their idea was to collect core samples of the ocean by a method known as shallow drilling. And then by looking at these cores, they could determine the composition of shelf sediments, assess sort of like the geotechnical capacity of the shelf to support man-made structures, and look for resources in there like oil or aquifers, which are subterranean deposits of rock or sediment that can absorb and collect groundwater, basically like a big sponge under the ground. And to that last point, the AMCOR survey and some subsequent drilling surveys did find evidence of aquifers with fresh water under the ocean. And admittedly, we have seen in other places, there's evidence of like these submarine aquifers. And they actually form either as pockets of glacial water that was buried by sea level rise after the last ice age, or as like sinks for groundwater runoff from adjacent land, or some combination of the two.
Do you think that fresh water is just sitting there and all the salt water is coming in and they're like, man, I really hate what's happening to the neighborhood with all this salt water, and like just really persnickety old.
So
it's ironic because they're salty.
I was going to say, so salt
Sorry.
salty.
Sorry.
Oh, that was
Typical.
good. Sorry,
Typical
I was so...
That was good.
I went into a very geologist point of mind, and I was like, oh man, in order to prevent a density inversion, because salt water would be more dense than the fresh water, so in order to prevent a density inversion where the salt water ends up on the bottom, obviously it must be, the fresh water must be locked up in hydrated minerals.
Wow.
I mean,
Cool.
obviously. But of course, this is where my brain goes, because
I love that your brain goes there, and just keep commenting with like all of that.
Is that like
so cool.
is that like the surface of Mars argument that like there's water that's locked up in mineral bonds that like you can't access, but like
there are hydrated minerals on Mars. Okay, I promise I'll talk
Go for it.
about this later as well.
Okay.
Because my whole thing was going to be like, well, let's talk about where water on Earth came from in the first place. And where else in the solar system is it?
It's God's
and
tears,
the
right?
water
It's God's tears. That's the story
what I
I've been
learned.
running with.
So many tears. He was just so disappointed.
In you. In whoever
Yes.
whoever
Did you
the
know
object is.
Did you know that the ancient Egyptians believed that when the god Ra cried, when his tears hit the sand, it created a bee? Facts
That's
machine.
poetic.
Giving you all the facts.
I did not know that. That's pretty cool, though.
What were we doing?
Wait, like a
If
honeybee?
you drank his tears, you could get buzzed.
Hey.
I swear we were doing something. Was it Emily's fact?
I
can't remember.
I will say I have a question for you guys, because I was
Okay.
kind of pondering this, like in researching this fact, like thinking about sort of these glacial waters that once, like 15,000 to 20,000 years ago, were in these majestic glaciers and that are now trapped underground in aquifers. Like, I have to wonder, did they feel subterranean homesick blues? Long setup. Worth it.
I love it.
I had a lot of fun with that.
No, totally
Drove
worth it.
that home. I love it.
There we go. But anyway, so back to the actual story. So since, as I mentioned before, those kind of drilling surveys consist of just poking little holes and examining samples that are taken from distant locations under the ocean, all those prior surveys didn't really give us a way of knowing whether the aquifers they found were kind of like isolated and discrete and scattered along the eastern seaboard, or whether they were part of like a larger continuous reservoir that spanned hundreds or even thousands of miles. And that is where study co-author, so the study that I'm talking about here, and Columbia geophysicist Carrie Key comes in.
I'm surprised that that scientist's, nominative determinism didn't turn him into a janitor if your name is Carrie Key.
Wow.
I was going to say he was a key contributor, but that just...
That works. That works. Well, he's a geophysicist.
Oh, well.
And he carries the key to the secrets of the world.
There we go. I like that's a good like business card slogan type thing. I like that. But yeah, so he basically developed or helped to develop a technology that involves electromagnetic imaging. And it was originally used for hydrocarbon exploration, which is like the fancy technical term for just looking for oil. But later in this publication, he uses it for aquifer exploration instead. And I kind of want to talk a little bit about that methodology because I think it's kind of cool, and I bet you guys will think so too. So these so-called marine electromagnetic methods, or EM, work kind of like a very sophisticated version of those handheld metal detectors used by beachcombing retirees, except that it scans the bottom of the ocean rather than a patch of sand in Florida somewhere, and it detects geological features rather than nickels, empty lighters, or, if you're lucky, a bent fork. But in the way that a metal detector uses electricity to emit a magnetic field and then detects changes to this field whenever it passes over a metal object, EM instruments, once they're submerged into the ocean, detect electromagnetic fields, and then they include a transmitter that puts out an artificial pulse of electromagnetism and a receiver that also records like the resultant waves as they resonate and interact with their undersea environment. So by analyzing the way that these waves react to the ocean floor, we can then gather clues about its composition and its layout. And as you might recall from high school physics, salt water is a better conductor of electricity than fresh water, so an area of fresh water can be detected by its higher resistance to these EM waves. So they pass through differently than they would in a saltwater medium. And the really important thing about this EM, this approach, is that unlike shallow drilling, it can survey and collect data over like a huge continuous swath of the continental shelf rather than just kind of like picking little bits and pieces here and there. So opting to take this less whole-based but arguably more holistic approach, Carrie Key, his graduate student Chloe Gustafson, and Rob Evans, a collaborator from Woods Hole, embarked on an expedition from southern New Jersey all the way up to Martha's Vineyard, encompassing the sites where shallow drilling had previously detected possible aquifers. And after 10 days of sailing and collecting measurements and occasional hiccups, kind of hilariously in the paper, which, well, not hilariously, but just to me in a way that felt kind of like very like truthful. The authors write that they lost some data in Martha's Vineyard because their instruments got caught in buoys and fishing gear. After all of that,
they didn't. They just went partying in Martha's Vineyard, hung out on the beach.
Maybe.
Oh yeah, we lost the data.
Had a clam bake, and we're like, yeah, I'll get it back afterwards. It's fine. But after all of that, partying or not, they had gathered evidence of a single gigantic submarine aquifer that stretches from at least New Jersey to Massachusetts and out to 50 miles offshore,
Wow.
with a total surface area of roughly 15,000 square miles.
Do we know, is it a particular color? Is it a yellow submarine aquifer?
There we go. I was like, where's the joke? It's coming. Where is it?
Sorry.
But yes, so that's massive. And admittedly, I don't know if this provides context because I also can't imagine the size of lakes. But if it does give any context to anyone, if you were to put this on, like basically on land, it would be like right between Lake Erie and Lake Michigan in size.
Decent.
Okay.
So
Decent.
she big. Yeah, it's
I think
solid,
that's great.
but it's not actually. It's porous.
Do you ever think about like what if eventually if we run out of like land-based or like above ground freshwater, that like we'd have to go do like deep sea well drilling for freshwater?
So that is actually part of why this finding is so exciting, because it creates an opportunity for that, where like, especially if it exists in like places where water is already scarce, or as you mentioned, like terrestrial sources are being depleted, it creates an opportunity to actually source not like fresh or nearly fresh water from this resource. And even though it's still salty, like its lower salinity still makes it a lot cheaper to filter than just plain oceanic salt water.
Okay, but like, what would be the consequences of like British Petroleum like oil well leak version of that, but for like fresh water in the ocean?
Ooh.
What would happen?
Like if like if the fresh water escapes.
Yeah, but like the whatever the
ocean.
wellhead or whatever happened at BP, like in the Gulf, that just like breaks, and then there's just like ridiculous amounts of like fresh water pouring into the salt water. What would happen?
Well, based on what Jessica said,
Go for it.
I'm guessing it would rise, but I think she'd know better.
I definitely think it would rise, and I think we also have to consider the effects of the ocean currents that are dominant in the Atlantic Ocean. Of course, you have the Gulf Stream that is taking water from the Gulf of Mexico and from the Caribbean and pushing it up along the East Coast, right where all of the drilling experiments took place, and then kind of shuffing it out. That's not a word. Shuffing it out into
Shuffing. No, I know that. It's a science term. Yeah, shuffing.
Yeah, totally.
Total science term. Yeah, shuffing it out into the middle of the Atlantic Ocean and even potentially reaching areas like England. You know, it's kind of famous for its relatively moderate climate, despite the fact that it's pretty high in latitude. So a lot of that is because of the Gulf Stream. So yeah, I think it would just, go up and then kind of get shoved out into the Atlantic. And that's probably what would happen to most of it. It would totally throw off a lot of the oceanographic models that people have. Like, what? Why is this water suddenly so much less salty than it should be?
Would you even notice that?
Where is it
Would you even
from?
notice the difference in salinity?
It depends on how often you sample salinity and from what places. But there are NASA satellites that monitor things like salinity, like wave height, like all even different temperatures, because I would assume that the temperature of the water in the aquifer is different from the temperature of the salt water around it as well. So maybe you would notice some kind of temperature anomaly in it. I don't know. I guess this is all theoretical, but we could see, I guess. I would be that would be really curious to find out.
I would love
actually.
for that to be the plot of a disaster movie. There's fresh water in the ocean. England's gonna be destroyed.
That sounds so quaint, I have to say.
That's what makes it better.
Yeah, it's like, oh, that's a problem. That's so cute.
Just all these
so
these big bloated fish, just washing ashore.
That would be a problem for a lot of the ocean life that needs salinity. And if it suddenly had only fresh water, and maybe you could have some animals that could go down to where the salt water was, but not all of them could do that. I guess it depends on how much the volume was and how quickly it came out.
Because I think there's a cool comparison, I think, because there's measurements because of glacial melt and runoff. There is a desalinization happening in the ocean, and I forget what it is. The introduction of maybe millions to hundreds of millions of gallons of water, which in the 100 million trillion gallons of the ocean, don't make a huge effect, but they're locally you get a much bigger difference. And so I don't know, that's a cool I don't do math anymore, but that's probably a second order equation that you could plug in there.
Sworn off it forever.
Oh, I'm sure. So I'm going to throw in a fun oceanography fact because I just think it's so cool. The unit that oceanographers use to describe the mass of water moving in a current like the Gulf Stream, or maybe as output from something like a river, that unit is actually called a sverdrup.
Ooh, that sounds Norwegian.
And it's a brief.
Ooh.
I just think it's one of the coolest names for a unit ever.
How does that spell?
Sverdrup. Sverdrup.
Cool.
Yeah, it's abbreviated as SV, and I just think it's so cool because, oh gosh, my oceanography professor is going to haunt me for this one. But
you have one of those, so it's fine. You're already ahead of us.
This was a few years ago, but the combined output from all of the world's rivers into all of the world's oceans is either 14 or 19 sverdrups. It's somewhere in that teen kind of range. And then the amount of water that moves in the Gulf Stream is something on the order of hundreds of sverdrups. Wow. To give you an idea of just how much water is moving in one of the major currents on Earth. And that kind of fact just blows my mind. Yeah. So, sorry, no joke, but cool fact.
Need.
Yeah.
With our podcast, it has to be one or the other.
I will strive to do both.
I'd like to see other things measured in sverdrups that shouldn't be. I can bring this up here very confidently. We're all familiar with the Boston molasses disaster.
Oh yes.
Yes.
In
Yes,
1919.
extremely
Where else in the
familiar.
world do you get 4 people who are just casually like,
Yeah.
oh, of course, yes.
I mean, I'm at least from Massachusetts.
Yeah.
I don't know what's up with you guys, but
Love molasses. It was
Fair
a
enough.
tragedy.
Pretty sure I
Like,
because so much molasses was wasted.
Yeah.
You monster.
but do you think that's a microsphere drip, probably, of fluid just right down?
maybe less.
Yeah, that's crazy.
You know, it's been too much time since I took these classes, so I couldn't tell you like how many kilograms cubed or kilograms per meters cubed that is, or what the density is, or what the volume is. But you know, I can look it up super
Who do you
quick.
think Sverdrup would have wanted to be president? Would he feel the Bernoulli? Okay, moving on.
I am Navier stoked by all of these fluid dynamic references.
That was really good.
Oh, what?
Do you know what a nightmare Navier-Stokes is?
Yeah,
Or
all
Navier?
the partials. I hate it.
Oh gosh, it's a nightmare equation. That was good.
Every now and then, that's what I'm here for.
Well, it's too bad we're gonna have to cut all this out.
Oh no.
We don't have time.
There's
Emily,
no
keep
room.
going.
Okay. So the last thing I wanted to mention was just like, so, I mean, the stories about this started coming out last summer, and I remember when I first saw it, I was just like thoroughly flabbergasted, even just from the headline alone. And it kind of stuck with me afterwards of like, I mean, there's all sorts of very cool science stuff going on, getting talked about every day. But I was kind of contemplating my reaction to this story in particular. And I think it stems from the fact that like, there's something about sort of like our observable planet to me that I think I'd kind of assumed that we understood a lot of everything around us, at least like immediately around us, like, oh yeah, the ocean, we get the ocean, the mountains, we get the mountains, as opposed to like outer space, which is infinite and like, at least to me, impossible to conceive of. But then in our next segment, Jessica's going to be like, space, and I'm going to be like, that's awesome.
Very high expectations.
Just a preview for everyone. And in the same way, too, as a molecular biologist, I also kind of have a similar-ish view at that more minute level of things, where it's like we have, you know, an understanding of it, but still, like, in the same way that we can't see it directly, I have more of an idea. There's so much still that we don't know, whereas, like, you go about the world and you assume that we know all of this stuff and there's not gigantic piles of water just lying under the ocean. But given that, anyways, that brought me to a quote that I thought I could end on that was also appropriate to this fact, to this theme, to that idea, which is, don't go chasing waterfalls. No, wait, it's the wrong one. Sorry. It's,
Don't go chasing water flows.
don't go chasing aquifers, except chasing.
Oh, that's even better.
But
Only stick to spare drop units. That
nice.
So I guess this decade I learned all about the water of the Earth and of Europa and asteroids, Pluto's moon Charon, exoplanets, you know, the water of the solar system. I mentioned on the beginning of this podcast that I spent years studying Europa. Europa is pretty famous not only in planetary science, but also in the general public because it has a global ocean underneath an ice shell. And we're not exactly sure how thin or thick this ice shell is, but it's probably between about 5 and 25 kilometers. In miles, let's see, that's between like 3 and...
3.1. That's a 5K.
Yeah, exactly. That's between like 3 and let's say 16 miles. Basically judging from 5K distances. So going off of something that Emily, I believe you said the aquifers, and they might all be interrelated to each other, and they might even be like connected at some level. In that same way, we're not 100% sure what the water looks like on Europa in terms of, is it only contained within the ocean, or are there little pockets within the ice shell? And if there are pockets within the ice shell, are they close enough to the surface that we could theoretically send a lander mission there and have it drill into the surface and actually sample the water directly? So super cool, obvious implications for potentially finding life outside of Earth. But I think the bigger question is, how did the water get there in the first place? And what else do we know about water in the solar system? Because it turns out this very familiar molecule that we all can rattle off the chemical formula for, H2O, it's actually a profound player in how the solar system came to be. So, in the beginning, there was a baby sun.
I always knew Jessica was God. In the beginning, there was water.
I put it there. You're welcome.
I guess I'm saying in the beginning of our solar system, there was a sun that burned a little bit bigger and a lot hotter than it does today. And it was surrounded by a cloud of gas and dust. And this cloud was not just a fluffy one in the sky. This was huge. This expanded all the way out to the edges of our solar system that we know today. And the gas, as it rotated around the sun, the gas and dust, the gas actually moved a little faster than the dust. And it created these little pockets of what are called instabilities. But basically, it's where things got messed up. We brought up the Navier-Stokes equation earlier, so think of that going completely haywire, and these little pockets formed, and that's where planets came from.
Can I ask real quick? I actually don't know what that is. I laughed along with everyone else.
So Navier-Stokes is a way to model the turbulences of a chaotic system, something like fluids going through a pipe or along a river, or like gas and dust orbiting a baby sun. And
Got it.
It created, not the equation itself, but there were these little, physics basically created these little pockets of calm, and that's where planets were born and grew into the sizes that they are today. And at the same time, the sun is kind of calming down. It's getting to where it is today in terms of size and temperature. But we have this gradient almost of planets going from near the sun to way, way distant to the sun, like even beyond Pluto into the region that's known as the Kuiper belt. So there's a line almost that you can draw in early solar system formation, and you can say in front of this line, everything is too hot and no water, no ice can solidify or liquefy, and everything within this line is dry. And then everything outside of that line, it's cool enough, it's far away from the sun enough that you can form things like ice. And this line is actually called the snow line.
Appropriate.
So,
Makes sense.
It's pretty straightforward. Geologists are maybe not the most creative people, but they're fun,
So the snow line is kind of like it's radiating outward from the sun. So everything within it is too hot and everything outside of it is too cold.
So is it just right?
Or is cold enough?
Cold enough. Yeah.
So it's kind of the opposite of Frozen, where Elsa just freezes everything around her, but then if you get far enough away from Elsa, the snow stops.
Yes.
Okay,
First
I got
Elsa.
it.
But-
Cool. Terms I can understand.
Yeah.
I'm here.
Yeah.
So I guess like Elsa lives beyond the snow line, and everything within the snow line, that's the sun's domain. I don't think there's a villain of sun. I don't know. Maybe the heat miser from that
Nemesis is our...
Oh, right.
I'm Mr. Heat Miser. Yeah.
Yes.
Yeah, that guy.
Great reference. Ugh.
Oh, that's such a great show. Anyway, okay, so you got Elsa and the Snow Miser chilling out in the outer solar system. You got the Heat Miser over by the sun, and then somewhere in the middle is the snow line. And inside a lot of these rocky planetesimals, the name that we call baby planets, they're forming within the snow line. And then outside you get the more ice-rich planetesimals. So that's where we think comets would have formed, and different meteorites that are more enriched in ice and water. And then Jupiter literally comes in from like far away from where it formed, and it comes into where Mars is, and it just moves around and it shakes everything up, and so stuff from the outer solar system gets flung into the inner solar system. So blame Jupiter.
Freaking Jupiter. Ugh, loves drama.
Anyway, so now we have set the stage for Earth to receive its water and actually grow into the Earth that we know it to be today. Around 3.8 billion years ago. So this is a really, really long time ago. At this point, we have the Earth-Moon collision event happened, and so Earth has its moon. It's starting to calm down, and it's getting its water. And it might have been there earlier, but the earliest we can track Earth's water is to about 3.8 billion years. So this is quite old. This is reaching very far back into Earth's history. And it's getting it from somewhere, because again, it formed within the snow line, so we think that all of the water that Earth had originally would have burned off, and it certainly would have burned off in the collision event, because as you can imagine, they're very high energy, there's a lot of heat, and that would have just burned off all of the water or ice that might have been on Earth in the first place. So we finally have Earth calm down to a point where it's accepting water, and the question is, where is it getting them from? Now, in the 90s, or actually, I would say, like, as long as people have been looking at comets, which might have even been like the 1600s, since the first telescopes were invented and people could actually see that, oh, it's a ball of ice and not just this streak across the sky. They were like, oh yeah, of course, comets are made of ice, the Earth needed water, therefore the comets brought the water to Earth. You know, totally easy, problem solved, done. Except it wasn't so easy, because we sent a bunch of missions to study the isotope compositions of comets, and it didn't work. I mean, the comet that we looked at didn't have the same isotope ratio as Earth's oceans, so that was a big surprise. You know, we thought we had this wrapped up in a neat little bow, and it turns out, nope, it's a lot more complicated than that. So we started looking for water from other sources. And one of these sources that we found, and I say we as planetary science, not me personally, but a lot of planetary scientists actually study meteorites, which are the bits and pieces from other planets and other destroyed worlds that have flown through space and through our atmosphere and been collected on the surface of Earth. So there are many, many, many different types of meteorites, and I'm not anywhere close to an expert on most of them. But I can say that the one that we want to talk about the most is one called a carbonaceous chondrite. What's really cool about these carbonaceous chondrite asteroids is that they have water in them, but it's not liquid water pockets like something like Europa or Earth might have. They're locked up in these minerals, these clay-based minerals called phyllosilicates. And I promise that is the last, like, it's the second to last complicated word I'm going to ask you. No, I'm sorry, but the last one is super cool. You'll like it. But yes, these phyllosilicates are just like graphite. They're sheets, actually, and they just have little water molecules that are actually kind of trapped within their crystal lattice. So they're locked in there. And there are multiple missions that are going to carbonaceous chondrite asteroids right now. There's the Japanese mission, Hayabusa 2, which is going to asteroid Ryugu, and it's actually there right now. And then there's the NASA OSIRIS-REx mission, which is currently at an asteroid called Bennu. And we're looking at these asteroids specifically because we want to determine what is their composition and how much water do they have. Are carbonaceous chondrite-rich asteroids actually good at, are they good sources of water in case we ever needed to do a long-term space mission?
So these asteroids, they're formed in our solar system, but they have I guess, why is their composition so totally different than Earth? From like a mineral point of view?
Well, we think it's because they formed outside of the snow line. So they must have formed in a different part of the solar system, and then they were thrown in when Jupiter decided to move around. So, and then they just got trapped in an orbit, whether it was around Earth as a near-Earth asteroid or in the asteroid belt itself. You know, they stabilized somewhere, and they've just been there ever since. So when we study asteroids, we're really looking at the history of the solar system from different places in the solar system and at different times. So it's a big puzzle, and every asteroid is an additional little piece of it. That's why I think they're cool.
Very cool.
It's like forensic astronomy, like just taking it all and putting it back together. That's super.
That Man, I want to be that when I grow up. Can I change? I changed my mind.
It's like
Well,
law
I mean, it's
and
funny
order
that
of
you-
magnitude, or like
Bum, bum.
very cold case.
Right. Very cold.
Nice.
Frigid. Well,
Yeah.
anyway, it turns out that we now wonder if asteroids could have been a source for Earth's water. Aha! But wait, there's more. Because this was an idea. Oh, I'm so glad you're loving this. Okay, 'cause
Yes.
there was an idea that I guess it's been kicking around for a while, but in the past 5 or 6 years, it's really picked up a lot of momentum. And it's the idea that there is a lot of water actually trapped in minerals within Earth's mantle. So in the structure of the Earth, you have the crust, which is the part that we all live on, and then right underneath it, we have the mantle, and then the outer core, and then we have the inner core. So the layer just below the crust, the mantle, is where we think a lot of water might be, just kind of wrapped up in different minerals, kind of like how the molecules in the water molecules in the phyllosilicates are wrapped up in the carbonaceous chondrite asteroids. We think something similar might be happening with the minerals on Earth. I can't really ask you to raise your hands, but I guess just say yes if you've ever heard of the rock cycle.
No.
So when geologists talk about the rock cycle, it's a cyclical chain of events where first a rock forms, say in something like a river environment, so it's a sedimentary rock, it's made out of sediments, and then it gets subducted through plate tectonics, so it's subjected to heat and intense pressure, and then it becomes a metamorphic rock. It has changed in terms of its structure and its appearance, and most often its characteristics as well. And then perhaps if it is really lucky, it then gets extruded out of a volcano as a volcanic or an igneous rock. And so the idea is that a single rock or a single mineral or even a single molecule can go through all of these different phases, and eventually the igneous rock gets worn down and it becomes deposited as a sedimentary rock again, and the whole cycle just keeps going. Sometimes the rock cycle isn't so straightforward as sedimentary to metamorphic to igneous. Sometimes it takes some detours, and one of these times, actually, I'm bringing up my notes, is a specific process called serpentinization. Ooh.
Cool.
Right, and that is the last complicated word I'm going to say on this podcast. So what happens in this process of serpentinization is that this igneous rock that existed beneath Earth's crust has gotten to the surface, but it doesn't quite make it out, and it actually gets buried again, and once again becomes a metamorphic rock. So instead of going out and coming back down, it's just kind of skipped the going out part, and it's like a teenager whose parents caught them sneaking out. That's, I guess, the best analogy
you go
that I
back
can
in
think
again
of at
and
this
then try to
moment.
sneak out again.
Eventually you do, because this is how we know about these rocks. So, that teenager is successful at some point. But what happens at some point is we have all of these igneous minerals that are specifically found within the igneous rocks, like peridotite, which, if you're familiar with the gemstone peridot, that's peridotite. And when peridotite is exposed to seawater, it actually changes its mineral structure into a mineral called serpentinite. And you might have guessed that the process that does this is something called serpentinization. So we have all of these, and we think that if we know of X amount of serpentinite and peridotite on the surface of Earth, maybe it's not too much of a stretch to think that there's a lot more serpentinite in Earth's mantle where we can't reach because it's just too far down, too hot, too high pressure. We would not survive, and instruments that we have right now would not survive. So we think then that there are hydrated minerals, so these water-rich minerals locked up in the mantle, and it potentially makes up a large part of Earth's interior, and some estimates even put it as much as 10 times the amount of water that we have in Earth's oceans is locked up in the mantle.
Whoa.
Yeah, it's great actually that now we have all these ideas for where water on Earth came from. Maybe it was actually holding on to it all the time. Maybe not as pure water, but as water that was locked up in minerals and have almost been locked away for 3.8 billion years or more. So that's what we have.
Let's just say, through a process we don't really need to elaborate on, that like there was something that was like leaching the water out of these minerals that are like deep in the earth. Let's just say all of a sudden they become, how do you say, would it be dehydrated? Would that be the word?
Yes, actually, the minerals.
So how would that affect the Earth?
Well, most of the rock cycle and most of plate tectonics actually, while we're not 100% sure how it works, we're pretty sure that it functions as a result of density inversions in Earth's mantle. So if you suddenly dehydrated all of these minerals, then what you would end up with is like a layer of water on top of a layer of very dense rock. And if it's stable like that, it's not going to want to move. So you might actually stop all plate tectonics on Earth. You would not have volcanic eruptions except in hot spots like Hawaii. But yeah, it wouldn't. Continents would stop moving. New crust would stop forming. That would be terrible for life on Earth, actually, because so much of our food chain actually depends on new rock coming out with new minerals that then get broken down by seawater and eaten up by the little phytoplankton. So if we lose out on the minerals that phytozoans need to survive, then we're going to kill the food chain.
Well, could I ask, is it safe to say, as like if you were an astrobiologist, is plate tectonics a requirement for life because of nutrient cycling, the way that like life would stop on Earth? Is that like a requirement you look for on an exoplanet?
I think, you know what? I think yes. I think I'm just going to come out and say yes, that if you want to have a world that can sustain life, and not just have it, but sustain it for long periods of time, you need to have plate tectonics. And I have a couple of different friends who are specifically studying whether or not an exoplanet or some exoplanets can have plate tectonics, and what kind of signatures we would need to look for to determine, yes or no on a planet.
That might be the hottest take that Fax Machine has ever had.
You heard it here, folks.
Yeah. Yeah.
Yes. Oh, I really hope that doesn't come back in the future
just,
to bite me in the butt.
We'll record a correction,
we'll see.
A retraction.
People do it all the time. I'm not worried. All right. Well, then I think I have said all that I can say right now about Earth's water and where it came from and how long it's been here, but it's definitely an interesting story, and it gets updated at least annually. So
awesome.
Definitely keep an eye on it.
So all that remains for us to do today is our watery quiz. So I have 8 questions for you of different fluid capacity, of which I hope you can splash around and find an answer.
Ew.
Yep, sorry. So
It's weirdly gross.
All right. Question number 1. According to the EPA, how many U.S. households use well water as their primary source of water? And for your answer, I just want you to be in the correct order of magnitude.
I do know a lot of people in Arizona, especially those that don't live in the city, they actually do pump their own well water. So that's pretty cool, actually.
I would think really anywhere that's like not near a lake or like a major reservoir, even a reservoir, I'm sure they could like pump it from somewhere and store it in a reservoir. So I would bet tens of millions.
I'm pretty comfortable saying on the order of tens of millions, though. People in like very rural Wyoming or Arizona or a lot of these western states would pull specifically from the Ogallala aquifer. So
you're locked in tens of millions. So you're totally right. Like the EPA says 13 million plus.
Wow.
They're not sure
that's
the exact number.
I have to admit, that's like less than I was going for, but I'm glad that tens of millions covers that.
Yeah. So you're right in there. And
yep, order of magnitude. Woo.
Nice.
So question number 2, I was gonna give you like a softball trivia question, and then I figured because Jessica's here, I could really ramp it up. So I'm gonna ask you a mini question on the way to the real question.
Wait, me specifically
The
or
whole group.
us?
It's collaborative. Yeah.
Yeah,
Okay.
we're all together going to answer this hardcore geology question.
So
Equal contributions here.
question number
Totally.
2. Kurt Vonnegut describes a theoretically deadly solid water called Ice 9 in his novel.
It's not Cat's Cradle, is
Yeah,
it?
it is Cat's Cradle.
It is?
Mm-hmm.
Good.
So
Okay.
he
I was like, I don't remember Ice 9 in Slaughterhouse-5, but I mean, maybe I got my numbers confused.
Wasn't it like a weather control thing?
I think it was like sort of like weather-driven warfare, like basically like cloud seeding.
Yeah. And it was
as a form of warfare.
essentially like
yeah.
DuPont chemical, or the equivalent in the book, made this like different water structure. But so that's your good job trivia question. Now we're going to ramp it up, geotechnical water scientist style. How many different structures of ice crystals have been actually formed in labs and might exist naturally throughout space?
17.
Okay, I have a series of hints that I was going to give you guys. And if you don't want to go with 17, I can still give you the hints.
Go ahead and give us the hints.
Okay.
Yeah.
So the first one is the most games won by any football team in a single season and postseason.
I remember, so let me just say, of course, well, you can give us more hints in a second, but I want to say that when we had Jessica like help us like with some science content for this podcast, she directed me towards the 17 kinds of ice. Then there were like Wikipedia pages about it, but there may be something in the question, you like how many have been created in labs or thought to exist or something that might be. So let's hear some more hints.
Okay. The second hint is it is the number of Shakespeare's sonnet in which he says, "Shall I compare thee to a summer's day?"
I feel like that was like 19 is emerging in my mind for some reason for that.
Ooh, maybe it is 19. Oh, that's embarrassing for me.
Could be totally wrong.
Okay.
But
hint number 3, and this one's kind of just straight up for Noah. The age Mary Shelley was when she wrote Frankenstein.
Oh, 18.
18. Okay.
So is it 18?
Oh.
I mean, we have 17, 18,
Okay.
19. It's not
Okay.
like we're not close.
Yes.
On tight
just-
ice, Rob.
We're,
just had her finger on the pulse right away. It's not 1 like many of our listeners may have thought. So it is in fact 18, and I'm gonna.
I bet
think
there's
I'm gonna
one that's like, oh, it could be technically A or B or something.
So ice 18 was first described in June of last year.
Oh,
so it is a
that's
new
actually
and-
new. That's
Wow.
new since we talked about it.
Yeah, so if you knew all your ice stuff as of June 2017 or 2019, this is new ice.
Wow.
This is some hot new ice.
new ice.
Wow.
You know what? I will take the L on that new ice. I am not.
No, we got
angry
it. We got
about it at
18. We
all.
rise and fall together. Mary Shelley.
That's
Yeah.
true, yeah.
And
Great.
just for the everyone else, the 2007 New England Patriots won all 16 regular season games, and then they won their 2 postseason games to get into the Super Bowl. So they won 18 games where they lost to the New York Giants on an amazing catch by Plaxico Burress as time expired.
Didn't Plaxico Burress shoot himself in the leg at a different occasion?
There are highs and lows in everyone's career. We're just gonna let that one slide.
On ice.
I remember that game.
It was a fantastic game. Then sonnet number 18, and Mary Shelley was 18 years old. And as
Shall
for
I
Ice
compare
9,
thee to a winter's day? Thou art more icy, and 18 kinds of you.
Nice.
Very different different poem. That relationship soured by the winter time.
Question number 3. This one, I figured Noah would talk a little bit about this. But question 3, deuterium is the form of hydrogen with a neutron in the nucleus, dramatically increasing its molecular weight. Because of this, hydrogen is actually the atom whose isotopes have the greatest variability in weight in terms of like total percentage weight. A glass of water made of pure deuterium or deuterium oxide is 11% heavier than just hydrogen oxide water.
That makes sense.
So in normal water, 1 in 41 million water molecules is D2O. How many molecules of semi-heavy water, which is 1 hydrogen and then 1 deuterium attached to an oxygen, are there per million water molecules?
Order of magnitude or what? Like, what do you want?
Yeah, order of magnitude. So I'm looking like over 1 million.
So the number of water molecules with one deuterium and one hydrogen on the oxygen. Okay. So
Yep.
Per million. I don't know why because then this is a probability question. That's awesome. So every 41 million you'd expect to have one of these heavy water molecules or these heavy hydrogens. So if you only have a million, then you only have a 1 in 41 chance of finding one of these heavy hydrogens. So I'm going to go and be bold and say 0.
Ooh.
0 is my answer.
So that is a really good answer for deuterium, but for semi-heavy water.
So basically like how? So the question kind of has to do with like where do we get heavy water from naturally? Like, are like neutrons whatever sort of bouncing around getting added to hydrogens, and then there's basically like sort of the probability you would have a full deuterium. It's sort of basically are the hydrogens getting added to like independently. So it really should it be like the square root of 141 million? 40, yeah, right?
Yeah, basically.
Because it has to be the independent likelihood of like one hydrogen getting an extra neutron and then the other one on that getting an extra neutron. So I'm not going to do the square root.
Okay.
That's it though, right?
But yes, you've unlocked the formula. So essentially
cool.
one in 3,200 or about 300 per million.
Interesting.
Molecules will be semi-heavy water. And
that's like a lot more than you think. Yeah.
Exactly.
Like,
yeah. Question number 4. 80% of what 2016 movie contained effects, basically special effects editing, and dynamic animation, making it one of the most CGI movies ever made.
Was there like an ocean movie that came out? It's like Deep Blue or
Finding
something.
Nemo. Finding Dory.
I'm imagining things. Blue Ocean.
So 2016, you're totally right that the reason that there was a physics solver in 80% of the scenes was because of water. Like, so water in this movie took on various shapes and interactions with the characters of the movie. Strong female lead with her own theme song.
Moana.
Yeah.
Oh, nice.
It's Moana.
Oh, cool.
Moana.
Oh, I
my
see.
gosh.
The water does stuff. Okay.
Oh, I can't believe that took me so long. I have to retire my Disney badge now. Oh, gosh.
Yeah. And so Moana is set in Polynesia, and the water is almost in every single shot. The ocean itself is a character. It like high fives people and has expressions and movements. And whenever the ship moves through the ocean, basically they had the background, which was, again, it was moving, but it was kind of set. And whatever happened in the foreground, the computers meshed together. So they created an interface that had to look natural. And in scenes where a storm was occurring, they had a physics solver determine the speed, mass, and trajectory of a ship and what would happen to the water. And there are literally scenes where billions of individual water molecules were generated and moved through the physics solver so that they would fall like real water.
Wow.
Which is a reason people are kind of funnily pointing out that Moana had a high carbon footprint for all the server time it used, despite being at heart like a very environmentally like green movie. So there's a kind of funny like you wasted so much carbon doing this. Question number 5: Gary White and what celebrity founded the Water Project, which aims to bring clean drinking water to afflicted people around the world?
Is it like Matt Damon?
It is
Matt
Damon.
Damon. That's
Okay.
right.
Okay.
Oh.
Okay.
So Matt Damon was a co-founder with Gary White, and it's actually a New York City-based nonprofit that works to distribute water and create sustainable water, basically water collecting practices. Okay, question number 6. This one's out there, and we're gonna go for it.
All right.
Alternatively described as alt pop, avant pop, and electro pop, what artist, whose name is one letter shy of that of a famous visual artist, and whose first and middle name are Jillian Rose, released her 3rd album last year, including If We Were Made of Water?
It's only one letter away from a famous visual artist, so it's not Lady Gaga.
No.
I was thinking of that joke the whole
who's
time.
Popular? Like all geologists, I'm just into rock. So Banksy?
Azalea
Banks. Yes.
So it's weirdly not Azalea Banks. It's an artist who just goes by Banks.
What?
Banks.
Okay.
Okay.
Yeah.
Oh, so the whole
And-
name only differs by one.
Yeah.
Okay.
Okay.
Wow.
And so Jillian Rose Banks.
Oh, right, Jillian Rose Banks. Oh, I don't know who that is.
Yeah,
Okay.
she's.
I no idea who that is.
I think it's safe to say that she's not that famous, but she's got way more Spotify listens than we do. So.
Ouch.
Oops.
Okay, fine.
Question number 7. According to the book Prisoners of Geography, what continent has the most miles of navigable rivers?
Well, certainly the Amazon River has like a billion tributaries. Certainly, like then you've got like the Mississippi going from the Great Lakes all the way down.
Yeah, navigable is throwing me off.
Yeah, that part I can't
Yeah.
speak to.
Or I think that's
Mississippi's not the
symbolic.
biggest,
No, I know. I'm just saying.
but then you have the Colorado.
But I'm
too.
thinking of like places that have like loads and loads of like solid-sized rivers flowing into them, and the Mississippi certainly is one of those as well. Like a lot of cities, especially in the Midwest, are like on rivers that then become the Mississippi.
I mean, Asia has a lot of rivers too,
Yeah.
because it's just got a bunch of
Yeah.
landmass and it just collects a lot
Oh
of
yeah,
rivers.
so we're also thinking of just the continent that has. So it's not even. So there's very larger continents that have the same density of say navigable rivers would have larger total. Good point.
Yeah.
Do we want to say Asia?
I think
then?
that's a pretty good reasoning. Yeah.
sure, yeah.
Locked
So
in.
guess is Asia. Believe it or not, it is North America.
Dang.
Okay.
And
No
So
kidding!
much of Mississippi, or
yeah, and so to put this in perspective, so a lot of the reason that a lot of other rivers are not navigable is because of waterfalls and because mountain ranges around the world really get in the way of most large river systems. The Mississippi River system, including all the tributaries, and honestly, if you take the tributaries, their distance totals more than the body of the Mississippi itself. If you take that entire river system, it alone is more than any other continent's navigable river distance. And then you can add every other river in the United States on top of
wow,
it.
dang.
That is so
Yeah.
We're
cool.
there, and then we
That's
didn't
nuts.
pump the brakes.
All right, question number 8 is the last question. And for this one, I wanted to do something about waterfalls. I was chasing waterfalls the whole quiz.
Shouldn't do that, Rob.
I heard that it's bad, but I don't really trust it. But so I have 3 waterfall facts. One of them is false. You have to tell me which of these waterfall facts is not true. So, number 1, Angel Falls in Venezuela is named after a maiden girl who fell off the edge and miraculously lived, some say carried by angels to the lower shore. 2, because of the volume of water and the lack of light pollution, because of the volume of water going over the edge, you can see moonbows during full moons over Victoria Falls. Or, in 1969, the state of New York closed the American Niagara Falls for cleaning.
Okay,
That's
that
true,
last
yeah.
one is true.
Here's the thing. I think we have to think about this analytically. Rob had to write this question. Did he A, find 3 facts, one of which has been like debunked, or like on the internet, say, or did he find 2 true facts and have to invent one about a famous waterfall? And so I think it could be the first, but I think we should at least consider that it may be the second and think which one is he most likely to have invented. I think the simplest one, which is not an insult to Rob, although come on, is the angels one. I think that like that would be the easiest to like make up. What do y'all think?
Well, I think moonbeams are or moon bows. I think moon bows are a real thing, and it makes sense that the tallest waterfall might enable a moon bow. So, from my physics perspective, yes, that makes sense that it could happen. And the other one, maybe it's just a folklore legend that's probably not true. So, you know how the early Spanish conquistadors like to embellish their stories.
Sure, I
so
sure do.
can't trust them.
Yeah.
All right, so
Don't
we're
we
saying
know
the angel
it?
falls.
Ah,
Okay.
Yep.
Well, I'll spend
I like
just
it.
a second on the buried lead on the fact that the United States closed Niagara Falls for cleaning at one point. And then second, I'd like to say a beautiful dissection of the art of making trivia. Because
This ain't my first rodeo, Rob.
But I did in fact find that because of the mass of water that's going over Victoria Falls, the highest volume of any waterfall in the world, that creates moonbows.
Yes!
On the regular.
Cool.
We did
Oh,
it!
good job, everyone.
And that's our quiz.
That was awesome. Thank you so
Yeah.
much.
Cool.
Great job, Rob.
So let me wrap up by saying to everyone, thank you for listening. And Jess, thank you so much for coming. It was absolutely wonderful to have you as a guest on this remote episode.
It was so much fun being here. Thank you all for having me.
So for everyone else, thanks for listening. You can check out our website, faxmachinepodcast.com, our Instagram and Twitter at faxmachinepod, and Facebook at faxmachinepodcast. And if you'd like to follow us on social media, I'm SweaterVestSCI, Noah.
At Arcs and Sciences.
At _EM Costa.
And Jess.
I am at Jessica Noviello, or you could follow me on Instagram on my at Road Trip Dinosaur Instagram account.
How did
Thank
we not
you.
talk about that?
Yeah.
Next time, Noah.
Next
Next
time.
time.
Next time.
There we go.
Always gotta
Gotta
save
leave him wanting
something.
more. Yeah.
All right. Fax Machine is produced by Rob Frawley, Noah Giberson, Emily Costa, with editing by Noah Giberson. Theme music is produced by Anthony Antonelli, and our logo is designed by Mike Zola. Thanks for listening, everybody. See you next time. Bye.
Bye.